And we are back for the second hour here on Monday, July 20th, Chapter 23, Part 2. And again, we're finishing it off here. Uh, we've only got a couple new reactions. Alkylation, we got the decarboxylation coming up. We'll see that with the malonic and the acetoacetic ester syntheses. Keep in mind these other reminders, especially test 2 due tonight. Very good. So let's go over here to the sideboard, look at this final halogenation reaction, so-called haloform reaction. You need a methyl ketone here, so it has to be a CH3 group. And remember, we said under basic conditions with halogenation, it's specific for iodide. That's what haloform, iodoform is kind of the key one here, although it will work with the others, bromine or chlorine. Excess, though, and you're going to form the triiodomethane. That's iodoform. You've heard of chloroform probably. That's a little more common. And that's trichloromethane or chloroform, the common word. And the sodium salt of the carboxylic acid. Okay. So it's a little bit different mechanism, except for this first part. We've already done this, enolate and then over halogenation. And then when you get 3 halides on there, especially iodide, it makes it a little easier to then add hydroxide here as a nucleophile. So this is a departure. So this carbonyl with a nucleophile. So this goes back to the earlier chapters, right? Tetrahedral intermediate. And then this can break down, right? And the leaving group here is a carbon coming off. Remember we said carbon can never leave. Well, if you have 3 halogens on there, it can leave. Why? Because this anion with 3 electron withdrawing groups on it can help stabilize that anion. And then this just grabs the proton off there, and you're in basic conditions, so you get that. It's not a preparatively useful reaction. It's an archaic reaction. It used to be a test for methyl ketones because the iodoform here is a solid yellow material that would precipitate out. Now we determine structure by NMR and modern techniques. But your book does show that, and I go through that. The only difference here is this tetrahedral intermediate here. Okay, let's get into alkylation reactions. Ones we need to know here are the reactions with alkyl halides. So let's revert that a little bit. I'd like to point out the utility of the bases that are involved here. So let's do an alkylation of a ketone, cyclohexanone, with potassium hydroxide and allyl bromide. So primary, leaving or secondary, I'll show you some secondaries that work here. And so what do we expect for the product? Well, enolate formation and then allylation, okay? Now, with sodium hydroxide, the problem is you don't only get mono, you get plus di, allyl, tri, and even some tetra. Even if you try to limit the amount here. And why is that? Well, this enolate right here is actually more stable than the initial enolate. Why? It's more substituted. And that's because the base is being formed under what? Reversible conditions, okay? So it's not favoring the enolate to begin with. And then once you form some of the more substituted alkylated enolates, those become more reactive and you get a lot of over-alkylated products. There are ways to limit that and to get a good enough yield of the mono, but most of the time with a reversible base like potassium hydroxide or sodium hydroxide, you're going to get over-alkylated product. But let's do it with LDA, okay? And then put in allyl bromide, okay? Now we get the mono only. Why? A couple things, right? So here we have what? An irreversible base. We're forming this completely. It's not enolate formation that can go back to the starting material. It's forming the enolate under irreversible conditions, and that's it. At that point, when you alkylate here, you get the mono product. You don't have any more LDA when you have one equivalent here to reform it, okay? Here with KOH or sodium hydroxide, you're forming some of this product in the presence of a lot more starting material, right? And so the enolate here, the more substituted one, becomes more reactive to give the over-alkylated thing. But with LDA, you form the enolate only irreversibly, Then you dump in the electrophile and you get the mono only in this case. For this substrate right here, sodium hydride or sodium amide would work just fine, okay? Now, if you take the mono substituted thing here and treat with more LDA, now what? You get the enolate on the other side. And we showed an example of this already. Now let's put in a different electrophile. Oh, how about ethyl bromide? Okay. So with LDA, we're forming a less substituted kinetic enolate, and now what's the product? Okay. Well, it's different, right? We get the allyl over here, and what? Our ethyl right there. Okay. Now let's take this mono product and treat it instead with an equivalent of sodium hydride base, and then ethyl bromide. What's the product now? Okay. Well, it's going to form the enolate right here because it's more substituted. This is a smaller base, it's a thermodynamic base, and we're going to get the ethyl where? We're going to get it right there. Okay. So you've got flexibility. You can form the 2,2 product or the 2,6 type product, okay, with complete selectivity over that. And yeah, you could even go nuts here. LDA, and how about isopropyl bromide? What would that give you? Well, less substitute spots. Well, this other side's blocked anyway, but it doesn't really matter. Ethyl, allyl, and then what? Isopropyl right there. Highly substituted ketone product, okay, with 3 alkylations, but handled correctly with a good substitution product. All right, so we got the reversibility issue there with the weaker bases. How about if we use a beta dicarbonyl compound? Let's take this diketone and treat it first with potassium hydroxide, 1 equivalent, okay, and then ethyl bromide. What do we get? And where do we form the enolate? Okay, so it's a couple issues here. And do we get over alkylation in this case, or is it monoalkylation? So there's a couple issues here. First of all, where do we form the enolate? Well, we form it right here. Okay, so we take the proton off there. And why is it there? Well, we've got resonance stabilization here and over here. Okay, and we can draw that delocalized anion like this if we want. Okay. We've got that fully delocalized thing. And so where is it nucleophilic? Well, it could be nucleophilic on oxygen or carbon, right? We didn't talk about that. And enolate has a lot of negative charge on the oxygen. It's a more electronegative thing. Why are we alkylating on carbon? Okay. Well, here's our product, and it's only mono in this case. So there's a couple things to talk about here. We don't get any of this. So we could, have our enolate here and say, well, how come we didn't get any allylation out there? This would give us this resonance stabilization here. Well, they always C-alkylate to give back the carbon-oxygen resonance. And also a carbon-carbon bond is more stable than a carbon-oxygen bond. There are electrophiles that will do alkylation on oxygen. We're not going to talk about those, okay? The halides will always C-alkylate for this class. That's all you need to know about there. But yeah, so forming the enolate right there and then C-alkylating right there for the reasons I just talked about there. Why no over-alkylation? Why no di, tri, or tetra? Because we could form more enolate out here, or what? Alkylate right there. Give the di one. Well, the pKa of this initial ketone, what is it? Remember we said a monoketone or aldehyde is about 20. But if you have the negative charge in between two, resonance stabilization, does the pKa go lower, higher, or is it the same? Right, it's lower. It's more acidic. The pKa is 10. It's a lot more acidic. Why? Because you have the resonance stabilized now between 2 electronegative oxygens. It's not quite as acidic as acetic acid. That's what, around 5. Here, though, it's 10, okay? And it alkylates on carbon. So that's an important thing to keep track of. Let's go to the overhead here briefly. Ruben, if you can adjust over here. Let me show you the application. The Evans alkylation here, Dave Evans at Harvard came up with this type of substrate here, an acyl oxazolidinone. It's called a chiral auxiliary. The stereocenter here is S. It comes from amino acids. The one from phenylalanine is the one that's important there. Or the one from valine is also used. You form the cyclic thing here, and then you acylate right there to form an amide, okay? That type of reaction we've seen before. Then you treat with strong base, LDA, form the enolate. And this enolate has an extra oxygen to coordinate the lithium and rigidify this part of the molecule. So if you look at it, it's right here. And then if you treat with a halide, primary, secondary, the halide comes on the enolate face opposite of where this big benzyl group is. The benzyl group's blocking the bottom part of the enolate. So you alkylate on top, and you get only the R stereocenter at that point right there, okay? Greater than 20-to-1 selectivity. There's two diastereomeric transition states. The one from the top is lower in energy, the one from the bottom, because the electrophile would have to come in next to the big bulky group. Sterically, that's slowing down the approach from the bottom face. So you get this product here, and then you can hydrolyze the amide to the acid, or LAH to the primary alcohol, with essentially one pure enantiomer, the R enantiomer. This ushered in the modern era of asymmetric synthesis for the last 30, 40 years, along with the sharpless epoxidation, the Evans chemistry. Show you an application of it to make this highly functionized amino acid. Has a beta alcohol and a butenyl group and another stereocenter right there. It starts with an Evans alkylation right here, forming this alkylated product, the enolate, blocking the bottom face, or the top face in this case, with the stereocenter up. And so this propargyl, this alkyne primary leaving group, comes in from the bottom. There's a lot of other steps I'm not going through, but that one stereocenter forms the other two stereocenters as asymmetric epoxidation going on there and opening it up with the amine, whatever. You can look through those details if you'd like. But I'd like to show you that application. That's used to make this commercial drug called Cyclosporine A. This is an immunosuppressant drug that's revolutionized organ transplant operations. So here's a harvested kidney from a donor that's going into a patient who needs a kidney transplant. The problem is, most of the time, even if the donor is a close relative or matched immune system-wise to the recipient, a lot of times the donated organ will be rejected by the patient, by the immune system. It's an overreaction of too much T-cell proliferation. If you can inhibit T-cell proliferation specifically with this potent drug, it's a cyclic undecapeptide. There's a lot of amino acids here, a lot of amide bonds. You can look through that. The key thing here is this unusual amino acid made using the Evans chemistry. Okay, so people receiving this drug, 90% of the time, they will not reject the organ. They'll be just fine. And like I said, even if it comes from a close relative, 80, 90% of the time, the organ will be rejected in the past. So this has really revolutionized that. Maybe you've heard about how these are transported around the country. There's a waiting list for people who need these harvested organs. But the cyclosporine immunosuppressant is needed to keep the body from rejecting that. Okay, let's go back to the board here and get into the malonate synthesis. So let's see. Malonate and acetoacetate. Alkylation chemistry will all be the same now. We'll combine this with decarboxylation to make any kind of carboxylic acid, okay? In fact, most of the carboxylic acids sold commercially are made using the malonic ester synthesis. All the intermediates are cheap and very efficient and very high yielding. Even though you can use LDA and some other bases to alkylate carboxylic acids and put other things together, it's more steps and more expensive. And we can also make all sorts of ketones using the acetoacetate ester synthesis. And it's the same idea here. We'll do the decarboxylation here and here with loss of CO2. That will be the new step here from the malonates and the acetoacetates. But all the rest of the stuff is the same. And I'll show you a real neat application, the barbiturate drugs, which are still in the pharmacopoeia. They're still used as sedatives I'll show you how those are made using the malonic ester synthesis and urea to form the cyclic barbiturate drugs. Anyway, so these are the cheap and efficient ways to do this. Let's get into it. So let's take our old friend malonic acid, which is this. Remember the oh my, such good apple pie? Well, here's the my part. This is malonic acid. And malonic acid has 2 carboxylic acids and 3 carbons, okay? And we're going to treat this first with methanol and acid. Well, this is just esterification. This goes back to chapter, 22. So we can form the methyl malonate ester, okay? So those are methyl groups on there. Very cheap, very efficient. You can make that very high yield. And then what? You take sodium methoxide. That's a base, but is this going to be reversible enolate formation or irreversible? Right, the pKa here is about 10, okay? The protonated form of this base is what? An alcohol. That's about 16, 17. So that's a favored reaction now. I'm drawing the arrow only in one direction. Why? Because this is now irreversible deprotonation. That base is strong enough to take this proton off, okay? So what do we get? We get the enolate. And I'll just draw it on the carbon. You can draw the resonance form of that if you'd like. But that's where our nucleophile is now. Now let's take that and treat it with ethyl bromide. And what do we get? Well, here's our alkylation. SN2, right? We have a nucleophile that's charged, and it's going to alkylate on carbon. Loss of the bromide, and it's going to give us ethyl malonate. Okay? Looks like that. Also a very high yielding reaction. Everything's very cheap and efficient there. Sodium methoxide. And this is often the same base as the ester. Okay? So you could say, well, methoxide's also adding to the carbonyl, giving a tetrahedral intermediate. Yeah, but that would be reversible. That would come right back and give the same methyl ester, right? What's irreversible is deprotonation, and that's completely here forming the resonance stabilized with the 2 carbonyls. And now the good alkylation event. And now let's treat with water and acid. Oh, we're doing another chapter 22 reaction, right? We're hydrolyzing the esters. And what's the hydrolysis product? Yeah, back to the malonic acid. Okay. So we form the acid to do a clean base reaction there. We need to have the methyl ester first, because if we tried to do the deprotonation and then alkylation directly on the carboxylic acid, we deprotonate here, and then that would be a lot of the nucleophile, right? Even if we added excess, we could form a triane in it, actually, but then the oxygen would be the dominant nucleophile and give us a lot of ethyl ester in that case. Okay, so the methyl ester is formed for a reason, to control the alkylation, and we get good monoalkylation there, okay? And then we take this and we heat it up, and we're going to say 100 degrees. I think on the overhead I said 80 degrees, and what occurs at this point? You decarboxylate, give this product. 1, 2, 3, 4, 1, 2, 3, 4 product plus CO2. Now that's the new step. That's decarboxylation. How does this reaction work? We're going to have to look at the mechanism there for a second. So let's see. We lose one of these molecules, carbon dioxide. And look, this hydrogen gets put right there. So there's 2 hydrogens back there. So that's all we're losing is the CO2. So how does this reaction work? Let's see. Well, let me redraw the diacid here. And I'm going to redraw the acid such that I've got a different conformation. But it's the same molecule as this, okay? I just rotated around here. And now I've got the proton on the other carboxylic acid next to this carbonyl. Now, when this is heated up, look, we can grab this proton off here, okay? And that's an intramolecular hydrogen bond. I think I mentioned that before. These electrons can come down here, And look, if these electrons are coming up, we can then push these electrons here and break this carbon-carbon bond, right? So look at that, the motion of electrons there is just 6 electrons moving around. Out of a pi bond, out of a sigma bond, and a sigma bond here, we're breaking 2 sigmas. Uh-oh. Well, that might be why we need the higher temperature, right? What does the product look like? Well, this oxygen up here has a hydrogen, and this carbon-carbon position has a double bond. The other OH is right there, it didn't change. The ethyl's still there, so where's the CO2? Ah, it's right here. You know, you can put that into a line now. That's now sp hybridized, right, for CO2. Why can we break 2 sigma bonds here and cleanly go to this type of reaction? Well, we get back a pi bond here. In fact, we're forming the most stable form of carbon, okay, CO2. That has a lot of enthalpy. And plus, it's a gas molecule, so we're changing the entropy, the randomness of the reaction in a favorable way. So it's a couple things there. Plus, we're getting back a pi bond here and a sigma bond there. But wait a minute, that's not the carboxylic acid. That's the carboxylic acid we want. So what's up with this intermediate? You can see the CO2, but what about this intermediate? Ah, look, that's just the tautomerization over to here, right? Because that's just changing the hydrogen from here and bringing it down here. And instead of having a carbon-carbon double bond, or an enol, you can say, we're putting the carbonyl between carbon and oxygen and moving the hydrogen there. It's just tautomerizing, okay? And we could draw that mechanism again, but we've already seen how that works. But when the malonic acid is heated up, okay, you lose CO2 and you form the monocarboxylic acid. You can't take both of them off. You just take the one carboxylic acid off. Why? Because that can help the reaction. It grabs the proton off the carboxylic acid that's eliminating. Protons transfer there, that allows for the formation of the new pi bond here, and then weakens this bond and allows that to break. This is the tough bond to break, right? This carbon-carbon bond. But once you have this arrangement here, it can happen in this concerted fashion. It's actually in the pericyclic family of reactions, the same family of reactions as the Diels-Alder. There's no charged intermediate here. We're just rearranging pi and sigma bonds, just like we did with Diels-Alder. So this reaction is allowed, especially if it's a 6-membered ring like this, and you have 6 electrons that are going around the ring. That's actually favorable electronically. And then, like I said, entropy-wise here can overcome that enthalpy, that strong bond that we need to break right there. But yeah, that's the mechanism of decarboxylation. Let's show how to do this with a couple of synthesis problems, and then we'll do some dialkylation malonate, and we'll get to acetoacetate. Let's say we want to make this carboxylic acid, and we want to make it from malonic ester. So we're skipping ahead. You can always start with the malonate ester, okay? The bond that's strategic is this one right here. So we'll be able to decide which electrophile we'll need here. Which base are we going to use? Well, we're going to use sodium methoxide. The base that corresponds to the ester, we're going to form this enolate then, okay? And so what electrophile do we need? Well, this is going to get decarboxylated eventually here. These 2 carbons here are going to be part of the target carboxylic acid. So right, we need a butyl straight chain one. Primary, butyl bromide or chloride or tosylate or whatever. That will give us the SN2 reaction, the alkylation event. And 1, 2, 3, 4 carbons, okay? Now that's not our final product. What do we need to do now? We need to hydrolyze, and you can just say acid and water. In fact, if you draw hydronium like that, we assume you know that you're in water. In fact, you can, well, let's do it stepwise here just to remind you. So just getting started on this. So that will give the malonic acid back that has now the butyl group on there. 1, 2, 3, 4. Count carbons, make sure you're okay. And then what do we need to do on the next step? Well, just heat. In fact, sometimes you can combine these 2 steps. If you just say acid and water and heat, you'll go directly to the decarboxylated product, okay? You can draw that transition state if you want for seeing how to lose CO2. But here we're looking at it in a synthesis point of view. That's the bond we need to make right there. And that comes from a butyl group, and then put it on there. All right, how about a dye-substituted one? Let's see. What if we want to make, not that one. How about if we want to make, how about this? An allyl and an ethyl. How do we make that from malonic acid? Well, let's go right to the ester. So there's our malonate ester. First step, sodium methoxide, one equivalent. And what do we want to put on first? Both of these bonds are strategic now because we have the two hydrogens. We have a methylene group here, two hydrogens we can remove. Let's do one first with alkyl bromide, okay? And then let's do another one, sodium methoxide again with what? Ethyl bromide or chloride, okay? What will that intermediate look like? And we can back up and make sure we understand this. So this is double alkylation. It happens one at a time though. This is step one. Step two is right there. Reform the enolate. Our first one would just look like this with the one allyl group on there. You see we have a second proton that can be removed, right? In another step. And that will let us put on the ethyl. And then what? Hydrolyze, like I said, with acid. And let's just do the thing all together. Here we'll go to the diacid. And then what? We'll lose CO2, okay? So you see how efficient these syntheses can be. Any type of complex carboxylic acid, you can think about these bonds that you can make, okay? It's got to be primary or secondary, so there are some limitations. But you can put the two on there and give the dialkylated malonic ester. Hydrolyze the ester. You have to hydrolyze, and you have to show heat in order to lose CO2. If you leave the heat out, you'll just go to the diacid with the two alkyl groups on there, okay? So the heat is part of it to lose that, and then go on to the final product. Let's look at a cyclic product. And this is kind of a neat one, I think. How would you make this carboxylic acid? With a cyclobutane group. And you might think, well, those are highly strained. And yeah, they are. There's angle strain there. But if you do two alkylations with those stable enolates, you can actually do these intramolecular. Well, the second alkylation is intramolecular. Let's see what it looks like. So start with methyl malonate. And the first thing is the base. In a practical sense, usually we put the base in for 20, 30 minutes, make sure we form all enolate, okay? Then you put in the electrophile. Why do you not put in the electrophile at the beginning? Because this is a nucleophile and it could just displace your halide group. So you put this in first and then slash, put in the electrophile, okay? You should just know that from a practical sense. And then what do we need? We need a dibromide with what? 3 carbons. 1 carbon is going to become 1 carbon in the cyclobutane, and then we need 3 more here. So after the first one, it'll look like this. Remember, you just had the one equivalent, so it'll just happen the one time, okay? And you need to be careful about that. You can control the concentration. Usually it's in THF or ether. And if you do it a little more dilute, you'll accentuate just the mono alkylation product. Because you see, potentially you could have more enolate displacing that, and that would lower your yield, right? So some practical issues here. And now our second thing is more base, okay? In a second operation, that'll form more enolate here, okay? And then what? Then you'll allow for that to occur. Now you have to be careful. This is a nucleophile. That could displace some of that. But the pKa here, remember, is 10. So that proton transfer is actually much faster than the bimolecular SN2, actually. So you can get away with it and still get a good yield. But that's some of the minor byproduct that you don't want. So what would it be then? Well, cyclobutane. Have I got the right number of carbons there? 1, 2, 3, 4. Yep. So we just formed the second bond right here. From that enolate, 1, 2, 3, 4. Yeah, the bromide coming off it. Then what do we need to do? Just acid and heat. Make sure we have the heat there. Hydrolyze to the malonic acid, and then with enough heat, we can lose CO2. Okay, so very versatile. We can form cyclic ones, even 3 and 4 membered rings. 5 and 6 are more common, but that would be what we need to do. Now let's look at the acetoacetate synthesis, which is a little bit different, but not much. Before we had the 2 carboxylic acids from malonic acid. Now we have acetoacetate. That's kind of a mouthful, AA, acetoacetate synthesis. And what this means is we start with a beta keto ester. We'll do ethyl ester here in this case. So at the beta position, we have that. So where does the name come from? Well, this is an aceto group right here, 2 carbon, like acetic acid, the acetyl group. And then where's the acetate? Well, it's right here, okay? And that's that. And what's the synthesis here? Well, we're going to alkylate and decarboxylate and make ketones. So let's see. Let's take sodium ethoxide. We're going to form the enolate. And again, it's beta keto. So this is resonance stabilized. And one equivalent will what? Irreversibly form that, because the pKa here is still 10, right? And the pKa of ethanol is 17. So it's highly favored for that. And that's all it's forming. No reversibility here, no equilibrium. Okay. That was with the simple ketones and aldehydes. But now with the beta keto esters and the malonic ester, it's complete irreversible thing. And let's do our old friend allyl bromide here. What do we get? We get allyl in the middle position, very high yielding. Now let's hydrolyze that with acid and water. And that's what, a 352 reaction in chapter 22, right? We'll get the acid. Looks like that. Okay. Now if we heat this up, we get the ketone with loss of CO2. Now how does that work again? Well, we can lose this carboxylic acid here, the elements of CO2, and transfer that proton. We're not losing the acyl group, okay? The only spot you can lose CO2 is off 1 there. The carboxylic acid is the only thing here. Remember with the malonate, we only lost it off 1 of the carboxylic acid. So how does this work? Let's redraw this maybe. And then you can go through the mechanism the same way. So that's the same intermediate, just redrawn. How does it work? Well, transfer the proton here, break that bond, bring this over, and then break that bond. That's the same thing. Okay. The intermediate might look a little bit different. Let's see. OH enol right there. Your allyl's still there. And CO2 right there. This is the enol, right, of the keto version. And again, what's this process called here? The enol to the ketone? Yeah, tautomerization. I showed you how that works before. Decarboxylation always generates the enol form of what's left behind, okay? And that's part of why the CO2 can come out there. But look, we've made a new ketone from the ethyl acetoacetate, okay? So it's similar to malonic ester synthesis, which was used to make acids. Now we're making ketones with different selectivity. And it could treat with LDA and do an alkylation out here, or sodium hydride, do alkylations right there. So it's a way to use that in a complementary sense there. Let's look at a couple other examples here. From a synthesis point of view, let's use the acetoacetate synthesis to make a couple things. How about this? Ketone. How would we make that? Starting with ethyl acetoacetate. Let's use what? Sodium ethoxide And which one do we want to put on first? Well, how about putting on the one that's a little more hindered? It's still primary there. Here's our strategic bonds, right? So let's do the isobutyl bromide or chloride, doesn't matter. That will give us this, where we've got 1, 2, 3, 4, yep, with the branching there. And then what else do we need to do? Well, more sodium ethoxide. And what do we need to put on now? 1, 2, 3, 4, 5. A pentyl group, right? We need to put on pentyl chloride in this case. And so we'll get this, ethyl acetoacetate with our isobutyl. And what? 1, 2, 3, 4, 5. Hopefully I counted up carbons correctly there. And then what do we need to do? Hydrolyze and heat. So I'm not showing the hydrolysis thing, but we get the carboxylic acid, and then what? Decarboxylation right there. And that would transfer that proton tautomerization to get a proton at that alpha position. And then, yeah, the isobutyl group and the 1, 2, the pentyl group on there. Yeah, so it's a way to make that ketone. So you can make cyclic ones also from that point of view. I think right now we can jump ahead to the drug synthesis here. So maybe we'll go back up to the yeah, Ruben, let's show them some fun stuff here. Well, I don't know how fun this is. If you're Elvis Presley, maybe this wasn't fun. It's funny how rock and roll and drugs intersect here. We've talked about this in a couple of spots here. Elvis had a problem with sedatives. It's part of the reason why he passed away so young there. So I've got one of his pictures. Well, it's a stamp there. The king of rock and roll met his demise with one of these. I think it was Barbiturate was one that he was taking. These are very good to treat different conditions here. These sedatives, they mimic the effect of GABA, which is gamma-aminobutyric acid. It's one of the key neurotransmitters. It's the calming neurotransmitter in the brain. So a lot of times these are prescribed for different indications here. Still in the pharmacopoeia, in fact, there's hundreds of these compounds that are known. They all have in common this barbituric acid core structure. Yeah, because of the two carbonyls here, these two NH groups are acidic enough to be deprotonated quite easily. And look, you have a malonic diamide type structure here, a 3-carbon unit, and this methylene can be functionalized too. These were developed by von Baer, German chemist, in the late 1800s, and the applications to medicine came much later. They have side effects of addiction and dependence, dizziness, and overdose potential. So, and if you're interested, you can read about that. But there's a number of them that are made and still in the clinic. I think all 5 of these are still used quite commonly. Secobarbital has this secondary alkyl group here on that position and an allyl group. Phenobarbital has a phenyl and an ethyl, and you can see some of these others here. There are sulfur versions here, sodium pentothal, truth serum. Yeah, they've been abused by a lot of people, unfortunately. Yeah, that's just a little variation up there. So here's how they're made. Yeah, they're made relatively simple. Actually, hundreds, thousands of these compounds have been tested for different applications. They're very good drug-like character. Their properties are water-soluble enough due to the polar part of the barbituric acid. And you can put on any kind of an alkyl group, including some more water-soluble type ones. I think all the ones shown here that hit the GABA receptor are all these non-polar groups here. But here's one here. Here's how Eli Lilly still makes secobarbital on ton scale. They start with malonic ester. So here's the dimethyl ester of malonic acid. Treat with sodium ethoxide and then the secondary bromide. And so, like I said, this is an SN2 reaction. It's kind of slow with the secondary bromide, but you can get a high yield of this right here. And this is what? Irreversible deprotonation. The pK is 10. Enolate forms cleanly. Substitution, high yield of that. Another step is to take the same base, sodium ethoxide, form a new enolate here. and then displace the allyl bromide to give this intermediate. And then here's the new reaction we haven't covered, but I think you can figure this out. This is chapter 22 type stuff, right? These are esters, and here you have urea, which has NH groups like an amine, right? So the lone pair here can what? Act as a nucleophile, attack, form your tetrahedral intermediate, right? I'll leave it to you to figure that out. Ruben's nodding his head. He thinks you can do it too. Okay. If you want to ask me about it, you can. It's not in your book. I think they took this part out of the book, but I think you can do it. Attack there, tetrahedral intermediate, bring the electrons back down, kick off methoxide, transfer the proton. That will give you the one amide on the one side, and then you do an intramolecular one on the other side. They don't happen spontaneously together. They're not synchronous that way. One new amide forms, and then the other amide forms in an intramolecular fashion to give the barbituric acid. Which one are we talking about? Yeah, secobarbital right here. So this first amide would form right there from the urea, and the second one from that. And yeah, this is urea. This is the waste product of higher animals. Excess nitrogen is excreted like this, but we can, of course, make urea a number of different ways and use it as an intermediate here to form the barbituric acid ring there, the six-membered ring. It's kind of a funny-looking molecule, right? 3 carbonyls there, but they're amide-like, and it is ionizable. Forget what the pKa is there. It's quite low. I think it's 8 or 9. So, you know, at pH 7, I think it's neutral. These are neutral here. You can exchange it with sulfur and deproton. So this is sodium salt. Sodium pentothal is a little more water soluble, a little more available in the body. It's good to have drugs that are non-polar because they'll tend to have a longer half-life, persist in the body for longer times, but you can see how you can make these other ones quite readily there from that secobarbital. Although phenobarbital, you can't make that. You can't take an alkylation of a phenyl group right there. So you can't use the malonic ester synthesis completely there for phenobarbital. That's a limitation. Can't do aromatic leaving groups. Has to be alkyl, sp3 primary or secondary. Anyway, yeah, you can work that and show some other syntheses. And just know the basics of the activity, right? So you're not going to memorize a bunch of the indications and side effects, or even Von Baer. Don't worry about him, or Elvis for that matter. Just the basics of the structure and how it might be made using the principles, the reaction that we've covered, which in this case is the malonic ester synthesis right there. Okay, good. I think we're okay with that. Good luck on the tests taking later tonight, and be reading ahead, right? Chapter 24, and then tomorrow, Tuesday, you have a couple things. So yeah, you're going to be working overtime tomorrow, sorry, to catch up here on chapter 23, get that homework done, and also a quiz. But we have recitation tomorrow, Tuesday, so zoom in and we can help you stay caught up on that. So very good. Good luck on the test. Take care.